Rosset from Tel Aviv University, and this is based on the work of my student Karen Levinstein, part of her PhD work. And it's going to be about this long, complicated title, Dating Ancient Splits in Phylogenetic Trees, and it's really more than an application, it's the application to try to date the human-Neanderthal split. So the motivating application, or maybe the only application of this, is for analyzing human mitochondrial DNA. And what we have for the mitochondrial DNA in general is that it's non-recombining, it's maternally inherited. So one thing we can say about, say, mitochondrial DNA of all humans in this room and all humans in general is that it actually sits on a true phylogenetic tree. We may not know it, but there is a true phylogenetic tree, and there is, for example, a single ancestor, which we may call mitochondrial Eve, who gave her mitochondrial DNA to all humans. So it's unlike the complications with recombination and autosomal DNA, there's a proper phylogenetic tree. And what the community has done over a long time is actually collected many human mitochondrial DNA, and basically we have a pretty high confidence and believable actual reconstruction of the phylogenetic tree of the human mitochondrial DNA. And I don't know how many people here know it, so I wanted to show it and talk about the tree a little bit. So this is, okay, so this is the PhyloTree website, and what we have here is a presentation of the human mitochondrial DNA tree with mitochondrial Eve up there at the root of the tree. And the leaves of this tree are not, the leaves of the true human mitochondrial tree are humans, extant humans. This is actually because the tree is very big, each one of the leaves here is actually a subtree, and we're going to look at one of the subtrees and see what they look like. But we can already see many things that may not be surprising to us looking at this tree. For example, all the people of European origin in this tree, in this room, most likely sit under this part of the tree. Actually, a couple of branches in this part of the tree. If we have East Asians or South Asians, then they sit in one of these two macro branches, M or N. And basically, all of these haplogroups, all of these subtrees, which are the result of the earlier splits in the tree. So all of these groups are only found in Africa. So we clearly see, for example, the out of Africa history of humans by looking at the mitochondrial DNA tree. So this is the out of Africa event. Actually, in the out of Africa, we have some branches. Under this, we have some branches that are also only found in Africa. So actually, we had an ancestral population out of which the out of Africa split. So we can see a lot of human history in this tree, but if we're more interested in data, then we can look, for example, here we went into R0, which, again, most Europeans would actually sit under R0. So now the tree is lying on its side, and we've gone down to this subtree. So we just see the path from the mitochondrial Eve to this subtree, and then we see the detailed subtree under R0. So if we go all the way to the right, here we see actual samples. So these are actually names of samples on NCBI of mitochondria samples. But our interest is on the fact that so some people have done the work, and we're going to assume that they knew what they're doing, and there's good reasons to assume that, though we won't get into the arguments why. But some people have done the work to reconstruct the tree, and reconstructing the tree is reconstructing the history of these sequences, the phylogeny of these sequences, and also reconstructing the mutations that have occurred. So these are the lists actually. So for example, here we see that in the split from R0, these two mutations, so each mutation is ancestral state, location of the mitochondrial genome, which is 16,000 base pairs, and derived state. So these two mutations occurred on the root of R0, basically, and so on. And we have a lot of things going on here, different colors, we have exclamation marks, we have parentheses. We're not going to worry about this, but just one thing I want to point out. There's two types of mutations, transitions between A and G and between C and T, and transversions, which are all other options. And in this notation, transitions have a capital letter at the end, and transversions, we have to find one, have a small here. Transversions have a small letter at the end, and we can already see that most of the mutations are transitions. So this is very important. It's going to be important for us, because if we only have transitions, then we can think of the genome state as being binary, switching between two states and not four states. Okay, so this is a very interesting topic, but it's not really our topic. Okay, so hopefully. So this is what the tree looks like. And when we analyze this, the information on this tree, which we just looked at it anecdotally, one thing that's clear is that it's not reasonable to assume that all 16,000 sites mutate at the same rate, because, for example, this is a histogram of mutation counts, and this histogram actually continues. It has a long tail. And this is much more than 2,000 loci that have 0 appearances as mutations on this tree, whereas we have ones with 15, 20, and even 30 mutations on the tree. And it's easy to convince ourselves that this is not what a Poisson distribution would look like, which this would have if the mutation rates were equal between sites. So it's easy to convince ourselves that the mutation rates are different at different sites, and any statistical analysis we do of this data would have to take this into account. And then the other thing I pointed out is that transversions are rare. Only about 4% of the mutations are transversions. So one thing that we might consider is thinking about the sequences as being only binary and considering only transitions, and basically ignoring transversions in our analysis. And we'll see why this is going to be useful for us. Okay, so this is what the human mitochondrial DNA tree looks like. And our challenge that we want to solve is actually not estimating this tree, but estimating divergence rate, mitochondrial divergence rate with other species. So our sort of generic situation is that we have this very big tree of modern humans. We have one or a small number of sequences from a different species, say Neanderthal or Denisova, where we have single-digit mitochondrial genomes from them. And our challenge is to estimate this long branch, right? This long branch is basically from humans. It could be from here or from here. This is mitochondrial Eve, so we could start from here or from here. It doesn't really matter. All the way back to the common ancestor of humans, the modern and archaic humans, and then back down to the sequence we observe on the Neanderthal side. So we have many tens of thousands of sequences here, and with a known tree. We have one or all of one sequences here, and our goal is to estimate this long branch. We want to estimate this point. It's equivalent to estimating the length of the branch. We assume we know this time and we know this time, so it's all equivalent. Okay, so we want to estimate the time of the split between the species. And one thing we want to try to do is we want to try to see how we can use the entire information we have on this side, which is tens of thousands of sequences. and do it in a computationally feasible and maybe statistically more or less reasonable way. So this is our goal here. Okay, so we want this to be scalable, so we're going to make some assumptions and see whether that allows us to really do this computation with the tens of thousands of sequences that we have. So one assumption we're going to make, which, as I said, we can argue about its accuracy, but for now we're just going to make it, is that that tree we saw on phylotree is actually accurate. So both its topology, for sure, the phylogenetic relationship, and the reconstructed mutations are actually accurate. So that is going to save us all the effort of integrating over the uncertainty in the reconstruction in that big tree. Of course, if we want to do time estimation, we have to assume something about the relationship between mutation counts and time. And the standard assumption is the molecular clock assumptions, meaning basically the rate of the process at which mutations happen doesn't change in time and space, right? It's the same everywhere in the tree. And that means that if I can estimate things, lengths of things in number of mutations, I have a fixed conversion of that to time. As I said, we're going to assume binary sequences. In other words, we are going to ignore transversions. Because there are only 4% of mutations, we believe that we can do that and maintain most of the information. And we are going to assume a Poisson process at each side. So even once we assumed binary sequences, it still doesn't mean that there's necessarily a Poisson process in each site. We also need a symmetry assumption that the rate of mutation from A to G is the same as the rate of mutation from G to A in each site. So if we assume that for each site, now we have a Poisson process. The number of mutations that happen at each site is basically Poisson distributed. Okay, oops. And of course, we know that it's not reasonable to assume that there's a common mutation rate for all sites, but that there's an individual mutation rate for each site. And these two assumptions that I noted in red are where what we do clearly differs from standard tools that people would use for inferring things from phylogenies. Or inferring phylogenetic information from sequences. So these are just two names of common tools. All of them would basically take sequences and they would integrate over all the uncertainty, and they would work with 4-state situations, not 2-state situations. So and that has substantial implications for the computational complexity. Okay, so let's take a step back and say that under our assumptions, what actually is the statistical formulation under our assumptions. So we assume that we know the reconstruction of the tree, meaning at each site we observe the actual number of mutations that have occurred. So what we observe on the big tree is in each site the number of mutations that have occurred, and this is a Poisson random variable with some rate that is individual to each site and we don't know it. Another thing that we have is that on the long branch that we're trying to estimate, we also have the same number of Poisson random variables, one per site. But the point is that we do not assume that we observe these random variables. Right? So these random variables, we say they have the same rate. However, we don't know how long that branch is. Right? So we express this as this P, which is the ratio between the total length of the big tree and the length of the small branch. So we also have this bunch of Poisson random variables on the small branch, but we do not observe the random variables. Why don't we observe the random variables? Because all we can observe is the state at the beginning of the branch, which is the human ancestor or the human leaf, and at the end of the branch, which is the Neanderthal sequence we have. Because this is now a long branch, unlike the branches in the human tree, which are all short. This is now a long branch. We do not assume that a single mutation has occurred, that 0 or 1 mutations have occurred in each site. So that means that by definition, what we see when we compare the two sequences, binary sequences, transitions only, so what we see is the parity of the Poisson, right? So if an even number of mutations have happened, we are back to the original state. If an odd number has occurred, then we've switched from A to G. So 2 mutations is A to G and G back to A. 4 mutations is doing that twice. 1 mutation is moving from A to G, or 3 mutations. So basically we observe the parity, which we call ZI, the parity of this unobserved random variable, and it's an easy calculation. I have it here, but I don't think I have time to show it. It's an easy calculation to show that if I have a random variable with rate p lambda, then the probability that it's odd is half minus half. The probability that the Poisson random variable with twice the rate would be 0. So it's actually a very cool exercise. I mean, you could do it by summing up series, or there's nice probabilistic arguments why that would be the probability that the Poisson would be odd or even. Okay, so that means that I know explicitly, in terms of my parameters, which are the lambdas and p, I know explicitly the distribution of x and the distribution of z, all my observed data. So I can think of this as just a statistical estimation problem, and my unknown parameters are these rates at each site, which I'm not really interested in, but are unknown to me. So I can think of them as nuisance parameters for my problem. And then the length of that branch of interest, or the relative length of that branch of interest, which is really what I'm after. A simple transformation of the time to the most recent common ancestor. I can explicitly write the likelihood. I have the Poisson part and the binomial Bernoulli part. And can I now do maximum likelihood estimation under our assumptions? But really, all the assumptions are already captured by this likelihood. So I mean, there's no reason why I can't. And it's a complicated expression, but it can be, of course, can be optimized. For example, I can calculate derivatives and find the normal equations. I see that I have here the lambda and the p mixed. So, for example, if I want to solve this, I can sweep over p. Sorry. So given p, this is just, each of these is just a univariate expression for lambda, which I can solve easily for lambda I. So I can sweep over values of p. For each value of p, I can find the lambda hats. And then I can find, for example, which value of p also complies with the n plus 1 equation. Or anyway, I can solve this and get maximum likelihood estimators. What we may ask ourselves is whether or not this is a good idea. Why wouldn't it be a good idea? What do we know, for example, about maximum likelihood estimation? This is also very relevant for other methods for tree reconstruction. We know that maximum likelihood estimation is a good idea when I have a small number of parameters and a large amount of data. I have asymptotic optimality results. But when I have a very large number of parameters, it's not obvious that maximum likelihood is a good way of estimating these parameters. And in this case, I have, for example, in the mitochondrial example, I have these 16,001 parameters here, right? I have a parameter per site plus the length of what I'm trying to estimate. So we can think of a different approach, which in the trade-off is going to say we're going to pay in additional assumptions, and we're going to gain in having many fewer parameters. So for example, we can assume a distribution over rates. I mean, we can think of this as making those rates lambda, making them random variables or random effects instead of parameters in our problem. And now our parameters are just the distribution of these random effects. And if we assume the random effects have a gamma distribution, then what we get is a negative binomial distribution for the x's. And we can integrate over this to get a parity probability. So what have we gained or what have we changed? Now we've written a problem instead of in terms of 3 parameters only. The parameters of the gamma distribution over the rates and our parameter of interest, which is the relative length of the additional arc. It's not particularly difficult to solve this either. What does this cost us? That we've added an assumption, right? This is a flexible distribution, but it's still a parametric assumption about what the rates behave like. This is a very standard assumption that people make, but it is an assumption. With this I can solve. For example, if I guess alpha and beta, I can solve a univariate equation for P, but basically I have a 3-parameter problem, so it's not difficult to find an optimum for. I haven't written the likelihood, but it's actually very similar, right? I have the negative binomial likelihood for the x's, and I have the Bernoulli likelihood for the z's. Okay, so basically these are 2 methods that I can use. And both of them use my assumptions. Critically, both of them use the list of assumptions that I made. And both of them are relatively easy to solve. I don't really pay in complexity for using all available sequences, because that's only captured through these X mutation counts in X. Okay, so let's just do a simulation to see if we've gained something. So our simulations basically create data that look exactly as if it was generated from phyllo tree. So we take the tree and we just regenerate mutations, and we add a long branch where we only observe the parity, and we want to compare how well we estimate p hat, right? Which is the length of that branch. So I described 2 methods. We have a 3rd method, doesn't matter the details. And we critically, we compare to BEAST, which is sort of the state-of-the-art phylogenetic reconstruction, but BEAST is only allowed to use 60 human samples. Why? Because if I give it much more than 60, then it's just never going to finish. Because the methodology includes integration of all possible reconstructions, as opposed to assuming a correct reconstruction. So I'm looking here at the benefit of using all data versus the benefit of doing the careful integration that BEAST does. And at least its simulation, it seems that it's substantially better to use the entire data than to use small subsets of 60, which is what BEAST does. And there seems to be a bias, a consistent bias. And okay, so the x-axis here is p, 100 times p. So this is p being 2% of the length of the tree, which is approximately, or here is approximately where we get the Neanderthal. Yeah, I mean the most recent ancestor with Neanderthal is ancient, but because we have 24,000 samples, we have a very long tree of modern humans. So 1% is approximately the distance to the Neanderthal, and 2% is approximately the distance to the Nisova. So this is the relevant range. If we go far beyond this range, then we see different behavior. For example, the maximum likelihood, which is the method 1, which is the orange ones, does perform badly when p gets bigger. So we do see the disadvantage of the maximum likelihood with many parameters, whereas the negative binomial, which is method 3, does very well throughout the relevant and also beyond the relevant part. Okay, so I'm doing well for time, I think. Yeah. So the last part is just to go and apply this to our motivating problem of estimating the time to most recent ancestor. And so we have it for Neanderthals, for Denisova, and for chimp. And the first column is BIS2 using 55 modern humans, which is sort of the published state-of-the-art and the known numbers in the literature. And what we see is that we get substantially shorter estimates using our method with the entire cohort of 24,000 sequences. So we get about 20% shorter for, so we shouldn't look at method 1, which is less reliable, but if we look here, the numbers are similar. We get about 20% shorter estimate for the Neanderthal and the Denisova splits, and we get even more. We get a much bigger difference for the estimate of the chimp split. So, yeah, so I mean, our simulations indicate that there is a positive bias here, and we indeed get much shorter estimates. So there's a lot of details that have been glossed over here. For example, this is now quoted in years, but really everything we do ends up giving estimates in mutations and not in years. So you need some calibration. There's a calibration process that that uses some consensus estimate of the rate of mutation overall. Can be argued with, and there might be other issues.
How sensitive are these estimates?
Sorry?
How sensitive are these estimates to model assumptions?
So this is model free, right? Well, we have the 5 assumptions that we always make. For example, that the tree is correct. If the reconstruction of a phylotree is incorrect, then what we do is very questionable. And then ignoring transversions. We have some simulations in the paper showing that ignoring transversions, for example, changing the transition to transversion rate, and doesn't affect results. So in that sense, in simulation, it seems that ignoring the transversions is not a big deal, and it makes sense that it wouldn't be a big deal to me. But yeah, this is under all of this is under our 5 initial assumptions. Beyond that, this is model free. This is modeling assumptions, and this is a model that works very well but doesn't make much statistical sense, so I didn't present it. But yeah, okay. Yeah, so that's it. Thanks.